My name is Sergey Maschenko. I'm from SharkNet Compute Canada, based at McMaster University. And today's presentation is about Meta running a large number of jobs conveniently. Here's the overview. I'll give you a typical usage scenario, and I will explain the algorithm, main features, commands, and the ways to install the package. At the end, there will be time for live demonstration, and at the very end, we'll have time for questions. Here is a typical usage scenario. Probably some of you have been in this situation. You need to compute lots of independent computation, thousands, maybe even millions. There are two specific examples from my recent experience. One of them is me helping researchers at McMaster University to set up computations of soil evolution model for different patches across the globe. So there are thousands and thousands of patches, and you need to compute thousands and thousands of things independently. Another example is from my own research I did a few years back, which is essentially a Monte Carlo setup to compute a global minimum from, it's a multidimensional optimization problem. More specifically, it's a random lens design. So how do you set up workflow for problems like this? At the very least, you want to automate submission of these computations. In simplest case, you submit them as independent jobs to the scheduler. So most of you probably know some bash scripting, so you can write a bash loop like this. In this particular case, I want to submit 5,000 jobs. And so 5,000 times I will execute this command as batch, my job script, and I will pass the index inside the job script. So I have to interpret the index inside the script. For example, that index can correspond to a line number in the table, in the list of things I want to compute. As you can see, what I'm trying to do here, to execute 5,000 times one after another as batch command, which is probably a bad idea. So if you try to do things like this on our clusters, you know, as batch can be quite slow, sometimes a few seconds each submission. So imagine 5,000 or even more if it's 500,000. So it becomes totally impractical, this approach. So it's very slow to start, but there is even more serious issue. Submitting so many jobs from each user, it's a big problem for the cluster, for the scheduler. It's too heavy load for the scheduler, which runs on the limited number of CPU cores using limited RAM. So if there are too many jobs coming from users, scheduler becomes sluggish and unresponsive, and which is bad for everyone. So this approach is really bad. Some of you may have heard about job array feature of our scheduler, which is Slurm. And the way it's described, it sounds like it's a good solution. It's an improvement over the previous setup. At the very least, you're saving on typing. Instead of typing the for loop, you type as batch -- array equal, and then you provide a range of indexes, the sub jobs you want to compute. Here's my job script. So only one as batch execution. And inside your job script, you have to interpret now this special variable, slurm array task ID. You can assign it to I index and then do exactly the same on the previous slide. For example, it can correspond to a particular line in the table, in the list of things you want to compute. Unfortunately, the reality is you're not really saving anything except for a little bit of less of typing. The problem is the array feature still results in each of these sub jobs to be executed one by one by the scheduler. So the scheduler load is pretty much the same. And because heavy scheduler load is such a big issue, some clusters like Gram or Beluga have a fairly small limit on how many jobs you can submit to the scheduler, which is only 1,000 for these two clusters. And this limit also applies to sub job array feature. You cannot submit more than 1,000 jobs using either approach. Again, the reason for that is to avoid heavy load on the scheduler. So how to tackle this problem? How to set up workflow which would be not heavy on the scheduler? An obvious solution would be to try to bundle up those small but very large number of independent computation. And that's the approach taken by known packages like GNU Parallel, and more specifically, I'll be focusing today on more sort of advanced version, GLOST. So what they do they bundle up these independent computation into a large parallel job. You go from one extreme, too many small jobs, to another extreme, one ginormous parallel job. So you completely eradicate the scheduler load issue, but you run into new and perhaps even more serious issue. The queue wait time can become sort of impractical. Just imagine if you want to run 1,000 independent computations, you can either submit as 1,000 serial jobs, and some of these jobs will start running almost right away, others will be joining shortly, so your throughput will be fairly good. Imagine the same 1,000 jobs you want to submit as a single 1,000-way MPI job, especially if you're not using rack, if you're using default allocation. On clusters like Graham, you might end up waiting weeks or even months before you get the very first result. So it can be very dramatic increase in queue wait time. So time to get to your results in this approach can be very, very bad or just impossible. So from my own experience running serial farms of this kind, and when I say farm, I mean running lots of independent computation. I decided I want to design a package which would take the best features from both approaches. And so that's how Meta was born. So in Meta approach, you submit a relatively small number of independent serial jobs. I call them meta jobs, each of which would process multiple independent computations. Similarly to Glost, each allocated CPU core would run multiple code instances. But unlike Glost, you're not bundling up CPU cores into one rigid large parallel job, which is so hard to schedule and run for the scheduler because it's so rigid. So Meta has both advantages of low overhead scheduler load and short queue wait time. And here's a short animation which shows how it works. So let's consider we have a fairly short list, 20 independent things you want to compute. It's organized as a list, as a table. Here's the time axis. And we're trying to solve these 20 computation using 4 meta jobs. These are 1, 2, 3, 4. They're grayed out. They're not allocated yet. We submit these jobs to the scheduler. And at some point, one of them gets allocated. And red means it's now active. Yellow, it's ready to compute. And so what it does, the meta job asks for the very first thing from the list of things to compute. Let's say it's case number 1. So important point here. This package assumes no knowledge of how long individual computations are. In fact, it assumes they're quite different. Some of them are shorter, some of them are longer. There is some distribution, which is perfectly fine. It's designed to work well under this situation. So we are right here on our time axis. We don't know yet exactly how long computation is. We're just moving on. And then once we finish, we ask for the next thing to compute. It's number 2. So we're moving on. And but before we are ready to accept the next case, let's say meta job number 2 became active. Now it's the one who is ready to accept the next case, which is case number 3. So between the two, now the meta job number 2 is ready to receive the next one. Next is this meta job, this meta job, this meta job would be, but now it's meta job 3, let's say, became active. So now it's turn to get the next workload. So between the 3, you can see who finishes first and then gets the next workload and so on. And we would get it here, but now the final meta job would start accepting workload. Another critical point here is not all meta jobs have to ever run to process all your computations. It is totally flexible. If scheduler or cluster is too busy, some of the meta jobs never start. As long as the runtime of your meta jobs are long enough, they can themselves process everything you need to process. Another important consequence, it's very reliable in the sense that if any meta job dies halfway, processing computation, at the worst case, you're going to lose that particular computation. Nothing else will be affected. Other meta jobs will process all the remaining things to compute. And by the way, even things which do fail, there is a very convenient way to resubmit everything which failed or never run automatically. I'll explain that later. So in this particular case, coming back to our scenario, we have 4 meta jobs, and between the 4, we keep processing the workload, and we do it in a dynamic workload balancing way. As you can see, we are all proceeding more or less with the same pace, all of the meta jobs. Doesn't matter how early or late they started, Doesn't matter how long or short things they accept. On average, they are proceeding roughly at the same pace, and they will finish roughly around the same time. If you remember, I mentioned there are 20 things to compute, so that will be the final one. So what happens next? So once the final 20th thing was allocated, our method job number 1 will ask for the next thing, and there is none. We already finished the list, so it will die earlier. So there will be no wasted CPU cycles. Same thing here. So by the time we get all our results, first of all, you can see they all finish more or less at the same time. And these gray rectangulars, it's not wasted because these method jobs, they know there is nothing to compute and they die earlier than otherwise they would be running. But so there is no wasted cycles here. This is a critical point. So let's compare side-by-side GLOST, which is MPI, large MPI job versus Meta Pro. So there is flexibility for Meta on both left side and on the right side. Flexibility on the left side results that queue wait time is much shorter because scheduler is free to schedule these independent jobs anytime it wants. Unlike GLOST, which has to allocate a giant enormous amount of resources and start all of them at the same time. Rank syncing causes long queue wait time because of the this inflexibility on the left side. On the right side, Meta approach is, again, it's more flexible, and that results in no wasted cycles. On the GLOST side, all the ranks, MPI ranks, have to wait for the slowest rank, which happens to be rank number 2. So all these red rectangulars are wasted CPU cycles. So GLOST is inflexible both left and right side, and it results both in long queue wait time and wasted CPU cycles at the end. On a more detailed level, how Meta algorithm is implemented, how can it achieve the same task as GLOST does without using MPI? And here's the explanation. So the whole thing is started by running the first command you're going to learn today, submit.run, and there is only one obligatory argument, how many meta jobs you want to submit. So n, in this case, as I just showed, they don't have to start at the same time. They are all independent. Let's consider one of them. What you have inside a meta job, you have a loop, internal loop. And at the beginning of each loop, there is only one single step which needs coordination between different meta job. And that, in terms of time spent within this purple area, is fraction of a second. So it's a tiny fraction of overall iteration time of your user code compute time. So overheads are extremely small. And just because we need to spend this tiny fraction of time per iteration inside each meta job, that's why GLOST is using MPI. So MPI is obviously a severe overkill. MPI is totally not needed. Instead, what I'm using in my package is a file system method. I'm using log file command, which serializes access to certain operation. More specifically, at the beginning of each loop, the meta job will serialize access to a tiny file which contains the current item number we want to compute from the long list. And it reads the value, it adds +1, it adopts that value, and then writes back the incremented value back to the file system. And because it's serialized, there is no danger that if more than 2 meta jobs try to do the same thing at the same time, there will be some kind of a problem. It's serialized, there are no problem. But because operation is such a short duration, the chances that 2 or 3 meta jobs will do it at the same time is very small. It's there just in case, but the overheads are extremely small. So as you can see here, file system method is very efficient, works very well, and there is absolutely no need for MPI the way GLOST is using MPI. So MPI is definitely an overkill with lots of serious issues associated with that. So in addition to things I just demonstrated, Meta has some very important advantages compared to other packages. As far as I know, this is the only package which has this super convenient feature, automated resubmit feature. So any of you who had to compute thousands or maybe hundreds of thousands of independent things, you would know sometimes some of them would fail. There is a typo if input conditions. There is maybe a crash, a node crash in the cluster. Maybe there is a bug in your code. And then good luck trying to figure out which a few things fail out of 100,000 things you try to compute and which didn't. so you can recompute them. So it's extremely time-consuming process. Meta package automated to the extreme. So what happens after you run your farm, serial farm, it's finished running, you submit a single command, resubmit, and then provide how many meta jobs you want to use for this resubmit. What will happen, it will analyze all the exit statuses of all the independent computations you did, which are already stored in the system. And also it will figure out which of the computation never happened because maybe your meta jobs didn't have enough of runtime. And it will resubmit all these things which still need to be computed as a new farm, absolutely fully automated way. It's very convenient feature. Just for this feature alone, I think many should consider this package. It really makes your life easier. There is another somewhat more technical but still important advantage of Meta, which results in even more efficiency compared to other approaches. So this comes from the fact that all the meta jobs constantly store not just exit statuses, but also individual runtime for each code execution. And then they're using this data to improve the efficiency. In a more detailed level, so all these runtimes are stored in a single file from all the meta jobs cumulatively. And once the list is long enough, more than 8 runtimes, the meta jobs use the list to make a conservative probabilistic estimate of how long runtime typically is. I already mentioned that we assume the runtimes are variable, they have some kind of distribution. So this is a probabilistic way to get a reasonably good estimate of how long runtime typically is. And it's 1/8 quantile. So 7 times out of 8, we get it right. So the actual runtime will be shorter than what we think it is. And only once every 8 estimates, you'll get it wrong. And that's already, it's very good thing we can use to improve efficiency. So let me explain how it happens. This is one of the meta job examples I showed earlier. Now I'm showing the explicit end of the meta job. So there is an end. Meta jobs, of course, they know how much time left before it dies, before it gets killed by the scheduler. So before it accepts the next workload, let's say number 18, it wants to know, will it have time to process it or not? Because if it mistakenly thinks it has time, start processing, and then it gets killed halfway, then you wasted a fraction of your resources. So what happens, each of the meta job does or makes up-to-date probabilistic analysis and figures out whether the conservative estimate of the runtime is longer or shorter of the time left compared to the time left. In this particular case, the estimate is longer, so it thinks it doesn't have time to compute this thing. So what it does, it dies earlier, so it wastes 0 cycles. Once out of 8 estimate, it will get it wrong, so there will be some resources wasted, but the waste goes down by a factor of 8. Just to give you an idea how much saving you can have, let's assume you run a giant serial farm, 1,000 meta jobs, and your typical computation, typical length of this rectangle is 1 hour. So if you don't have this probabilistic estimator feature, you would, at the end of the meta job, all of them will start dying. And let's say you have so many things to compute that all of them will start dying while processing one of my cases. That means on average, I will waste half a CPU hour per meta job. There are 1,000 of them. So totally, I will waste 500 CPU hours or around 3 CPU weeks, which is a lot of resources wasted. But because of this probabilistic feature, I cut that waste by a factor of 8. So it's more like 2.5 CPU days wasted, which is bad, but it's tiny fraction, much less than 1% of the total utilization of the resources by the serial farm. So it's totally acceptable. It's like 0.1% total acceptable waste. So this is another important advantage. So what are the main features of Meta in terms of usage? What I described so far, I call it the default Meta mode. There is also a simpler mode of 1 job for each code execution, for each line in your table. You use it when your individual executions are relatively long, let's say 2-3 hours, and you don't have too many to compute, let's say less than 1,000. But why would you use Meta package for this in this case? Because you might still want to make use of this convenient resubmit feature and some other convenient features. So it's fine. You can use either Meta mode or simpler mode. I'm going to explain how a bit later. So the resubmit feature is one of the best selling features of this package, but also it has ability to independently operate multiple farms on the same cluster. I'll show how. Very importantly, unlike Ghost, we can actually run any kind of jobs, not just serial, but multi-threaded, MPI, or GPU jobs. So your jobs can be of any kind, and it's very easy. There are very minor changes you have to do, basically change the Slurm parameters, the way you would have to do it anyway, if you run it yourself. I mentioned exit status timings are captured for each code execution. It's used for internal consumption, but you can use it for your own analysis as well. So if you want to plot a histogram of all timings for all individual computations, the information is there. And there is a convenient way to analyze exit status to find the ones who failed, and then hopefully you can fix it and then resubmit it automatically. There are also additional commands, which I will explain in a second. So here's the list of the commands. The main one is submit.run. The only obligatory argument is number of meta jobs, if it's a positive integer. And if it's a -1, -1, it's a simpler mode, one job for each computation. Be careful with this mode. It will literally submit as many jobs as there are lines on your list of things to compute. So this command submits the farm to the scheduler. You can also provide optional as batch arguments here, but probably you would typically put them in a job script, as I will explain later. So resubmit command resubmits all computations which failed or never ran as a new farm. Can only be executed after the previous run is completed. But if you by mistake try to run it too soon, nothing bad will happen. It just will tell you can't do that. You can resubmit as many times as needed. And the arguments are the same as submit.run. They do not have to match the arguments from the submit run. So you can change number of meta jobs, etc. The other auxiliary commands, list.run. If number of meta jobs you submit is fairly small, this is the one to use. It will list all the jobs belonging to this farm and with the current state. For larger serial farms, it's more convenient to use query.run. We'll provide a one-line summary, number of queued, running, and finished jobs. So usually it's more convenient. There is very dangerous command kill.run. Without any prompt, basically it will kill all the jobs belonging to this particular farm. So be very careful with this command. And there is also option to prune, only remove the queue jobs. Very useful status.run with a capital S, especially if you use with -f. So all the things which have been already computed are being analyzed and presented. The exit status are presented. And if you say -f, it will list at the very bottom any non-zero status lines. So it's an easy way to spot if there are any problems in your hundreds of thousands computations. And it also tells you which line on your list corresponds to, so you can easily identify which cases were the problem, the culprit. And there is also clean.run if you want to completely clean this subdirectory and use for a new farm computations. Important notes, meta commands have to be executed inside a farm directory. There may be more than one farm directory, so you can operate more than one farm at the same time. So the way you operate them, you switch, you CD from one subdirectory to another farm subdirectory. And there you execute any of the commands I mentioned so far. Importantly, by default, a new subdirectory is created inside the farm root directory, is created for each independent computation. This is the safest behavior. That's why it's default one. If you compute thousands of things, it's probably fine. If you compute hundreds of thousands, you probably don't want to create hundreds of thousands subdirectories. There is an easy way to change this default behavior, and I will explain later. So how to install Meta? Meta is not available yet as a module package. It will be at some point. The way you install it on any of the national systems, you log into the cluster and then you do git clone, and here's the address. It's very convenient to move all the commands I just described inside a common bin subdirectory, typically in your home file system, and make sure it's on your path. So all of these commands are available and executable anywhere. So, and what you do next, you copy your code initial conditions to this meta directory, which was created when you did git clone. It's the default name, meta directory. Or alternatively, usually it's more convenient to use full path or relative path for your code. and initial conditions. Then you don't have to copy files. A critical step is to create a list of independent computations, which always has the same name, table.dat. This is a text file. Each line describes one independent computation. You can use more than one bash commands on the same line. You have to separate them with semicolon. And it's allowed to use redirects and pipes. Next, what you have to do, you have to modify jobscript.sh file, which is already present inside your meta subdirectory. And basically, you modify slurm arguments, runtime, how many CPU cores, how much memory. So these slurm properties will be applied to all of your meta jobs. At the very least, you have to change the account's name because the default one is a wrong one. You might have to modify single case.sh. I will explain later when and if you need to do that. In simplest case, you don't have to. And that's it, basically. If you want to run another farm concurrently with the first one, you just create another subdirectory, let's say meta1, and then you copy these two .sh files there, and then you create a new list of things to compute. And that's how we use meta. You change directory to a specific farm subdirectory, and then either you submit certain number of meta jobs, submit.run, in this case 8, or if you use simpler mode, 1 job per computation, you say submit -1. And then you can use any of the commands already listed or gave you in the previous slides. Just make sure you are in a specific subdirectory corresponding to this particular form. So what about these two .sh files? So the first one is jobscript.sh file. The only thing you want to change here is the sbatch arguments, the runtime for your meta job, how much memory it's using. At the very least, you want to change account name. It's either your default, supervisor, or maybe a rack account name. If it's MPI, you add, MPI specific terms, GPU specific, etc. So these are the only changes. Don't touch things here. You're not supposed to change any of these. And what about the second .sh file? As I mentioned, by default, you can use it as is. But for example, if you don't like the default behavior that it creates subdirectory for each computation and it goes inside there and executes the code and then comes back. So what you have to do, you have to modify a bit things between these two lines, which are customizable. And basically, you have to remove these two lines. So you don't want to make directory or just comment out, put a number sign. You don't want to change directory and you comment out this line. You don't want to come back. So these 3 lines, you comment out, and then all your computations will be executed inside the same directory, the farm root directory. Just make sure it's safe to do. Many research codes would create files of the same name. In that case, you cannot do this. You really want to do it in individual subdirectories. But if you took care of that, you make sure each run of your code creates files with unique names, then it's probably a good idea to run everything within a single level of your subdirectory. All right, and what about table.dot? This is the list of things to be computed. So typically you would put either absolute path to your code and then change in arguments, or you can maybe copy a unique name input file, save it as a standard name, and then execute. You use semicolon and then execute your code. Or maybe you use, if your code is in the path, you can just use without, as is, just the code name. And then you can use redirect. And remember, default behavior, you're doing it inside subdirectory below the farm directory. So if you placed all your initial condition files in the root farm directory, then you redirect from one level up. So you say ... But otherwise, you put any executable command. These are all okay to be used as table.dot lines. All right, now it's time to switch to live demonstration. What you should see now is my terminal, which is Mobaxtern under Windows. And in fact, I have 3 different tabs open. If I have time, I'll show you how to run more than one farm concurrently. I already logged into Graham cluster. I already did the git clone command, and I have this meta subdirectory. But before I show you the meta subdirectory, let me show the code I'm going to run today. It's a very simplified traveling salesman person solver. If some of you may be not familiar with this problem, given a list of n number of cities, let's say there are 15 cities randomly located, You start from one city, you travel using straight lines, and your task is to visit each city once and come back to original point, and you want to find the shortest possible itinerary. This is NP difficult problem, so it's very difficult to solve if number of cities is large. And I'm using basically a Monte Carlo simulation to do brute force computation. I do random reshuffling of the list of the cities, and then I use a unique seed number. So the parameters I will need the seed number, which each of the computation I have to provide a unique seed number, original for random number generation, and then output file name, let's say out.dat. It gives you some intermediate results. Here's the distance, here's the list of cities indexes. So it does reshuffling. So it takes roughly 11-12 seconds for one of these execution. And here's the distance. So what I want to do, I want to run lots of, let's say 400 instances of these computations, and then find the best result, the best itinerary. This is a Monte Carlo way of solving a sort of global optimization problem. So this is my code, and I am going to my meta1. I already renamed this directory. So by default, there are these 2.sh files. And in fact, I want to delete this table.dat. I want to show how I make one. So again, so what should I do? How do I create this table.dat in this situation? So I'm going to provide a full path to the code and TSP. And this is the seed number. And let's say I'm going to use just the same name of the file for my execution. So this is what I want to repeat 400 times using unique seed numbers. A very easy way to automate creation of this list is to use bash for loop. So I'm going to say I equal 1. I don't want to use 0 for seed number because it has special meaning. I less than equal 400, and then I plus plus. So I want to do this execution, and then I want to print this statement. So I'm going to do echo, put it in quotation mark, and done. So one thing is still missing here. I want to make sure seed number is unique for each line. And the easy way to achieve that, I'm just using $i, my index. That's it. So it produced 400 statements, which I want to execute. They're all independent. All I have to do is just to save it as table.dat file. Done. So now the only thing I need to change jobs script, I have to modify as batch arguments. I already know 30 minutes is more than enough for meta jobs. So I will be submitting 32 meta jobs to solve 400 very short computations. I'm using 4 GB of memory. When you do that, you're going to use actual account name, but because I made special reservation for this webinar, I'm using special account name and special reservation. That's all I had to do. And I'm not going to touch, so we're going to use default behavior, single case.sh. So all I have to do now is submit.run, and I want to use 32 meta jobs to compute 400 individual computations. So once you submitted all of your meta jobs, you can use standard SQ command, right? It's going to list the status. All of them are already running because it's a reservation. Normally would wait probably a few minutes before first of them start running. But it's much more convenient to use either list.run because this will only list jobs belonging to this particular farm. So output looks similar, or probably more conveniently to use query command. So right now there are 32 running jobs, 0 queue jobs, and 0 jobs which finished running. If you have a look what's going on, it's already computing things and it's creating subdirectory for each individual computation. And inside each of these subdirectories, one output file. You can list all the outputs. If they're single line outputs, you can do something like this: run asterisk out.dat. It's going to list everything which you have computed so far. Then maybe you can sort it, listing the shortest distance at the bottom. So you already can see finding the best, probably the actual global minimum. So because the results are identical for many of these code computation. That was one experiment. So let's try another thing. So let's see. We're still running all 32 jobs. If something goes wrong, or let's say you run out runtime. So we just runtime finish. We'll emulate this by just killing everything. So let's kill everything. So if you say query, it knows how many things have been processed, how many things haven't been processed, 161, either haven't processed or failed. And it tells you what to do. You run resubmit run, just use a new number of meta jobs. Yeah, let's do that. Let's do resubmit. Resubmit.run using, again, 32. It doesn't have to be the same, maybe 60 in this case, or even 80. I don't want to wait too long. So it's up to you how many meta jobs you want to use, resubmit and submit. They don't have to match. And then again, query would tell me how many are running. So you can use status, but right now status will all be 0 for all these computations we've done so far. If you say -F, it will try to list non-zero at the bottom, but because there are none, it's not gonna happen. So while it's running, I'm gonna show another thing. I'm gonna go to another subdirectory. In fact, I want to switch my tab. So I'm already inside meta 2. Okay, let me go back. So what I need to do, if I want to start a new farm, I just have to copy the 2.sh files basically into my meta 2. So I'm switching to meta 2 subdirectory. Now, whatever commands I execute will operate on meta 2 farm. It's a second farm. So what I'm trying to demonstrate now, how about we don't want to create subdirectory for each independent computation. So what to do? First of all, I have to slightly change my code execution command. So instead of saying home sym code tsp, let's say one out dot, I want to give unique name for each of these output files. So it would be safe to make all the executions within the same subdirectory. And there is an easy way to do this. So in the same for loop, I equals 0, I less than, not 0, I want to have 1, is an equal 400, I plus plus, I do the same echo. So the only change compared to the previous case, so my seed number is unique, but I also use unique output name, and the easy way to achieve is $i. So now all the output names will be unique, as you can see here. So now it's safe to run any number of these executions in the same directory. And then all I have to do is to redirect it to table.dat. And now I can run. Okay, and this was one thing. Sorry, there is one more thing. Then I go inside the single case.sh. Remember, I mentioned sometimes you want to customize. So I'm going to comment out the 3 lines I mentioned before. This one, which creates directory, change directory, and change back. So now I modified my table.dat, I modified this script, and now it's safe to not create subdirectories. So let's say I'm going to use 8. And they're already running. And if you list files, you can see, well, no, it was too soon. You have to wait at least 10 seconds. So now each of these computations are not creating subdirectory. Instead, the results are just stored in the same root directory. And if you want to see the result, so you want to do something like this, sort. So this is another way. All right. And then I want to show one more situation. What if you need to compute hundreds of thousands of things or millions of things? You definitely don't want to use the default behavior. You can't create millions of subdirectories and millions of files. It just won't be possible. We have a limit because there's so much overhead on the file system to have millions of files. So you just can't do that. So you have to change behavior slightly. So we're gonna address this issue now. So again, we're copying the 2.sh files into yet another meta 3 subdirectory. And we are switching into meta 3 subdirectory now. So what we want to do, we want to, instead of single case.sh script executing literally line by line what's written in your table.dat, which is default behavior, and it's achieved by this command. Instead, we're going to comment it out. And instead, we're going to write explicitly which commands you want to execute. And we will make use of these 3 special variables provided to you. So you can customize execution. So you're gonna say full path to your code. And I'm using different name for my code. I'll explain why in a second. TSP.2, TSP2. And then I'll provide argument $ID. So each line of my table dot corresponds to a different value of this variable. So I can say $ID, and that means the seed number will be unique for each execution of this command. And then I need to provide output file name. So what I'm gonna do, I'm gonna use out underscore, but I'm not gonna use this one. I don't want to create millions of tiny files. I want to create 1 file per meta job, and number of meta jobs is much smaller. And here's the variable I'm gonna use for that. So this variable has unique value per meta job, and there are just 8 or 32, a relatively small number of them. Okay, and that would work only if I modify, by the way, someone I think already noted there was a typo. This will only work if I modify my code, that instead of creating this file every time you run your code, it will append. If it already existed, it will append to the existing file. So you have to do 2 things. You have to modify the script, and you have to make sure your code can append rather than overwriting and overwriting. And that means any particular meta job will be appended to this file, which has this unique name per meta job. And at the end, you will create not millions of tiny files. You'll create just maybe dozens or hundreds of output files, 1 per meta job. And I already modified my TSP code. So indeed, it will work as I just explained. So code TSP2, let's say 1, and let's say out dot. So it will run the computation. And if I run it again, give me another 10 seconds. Takes another. Using different seed number, using the same output name. And because I changed my code, instead of using W basically mode in my C code, I use A mode, append. It's a very easy fix. And I ended up creating this file, which now contains both computation. Of course, if your file contains a bunch of lines, not just 1 line, things can get a bit complicated, but it gives you an idea. So if you can bundle up outputs of the files, you have to do that. And basically, this is the only way to do it if you want to run millions of computations. You have to bundle them up, so there will be 1 per meta job, not 1 per computation. So what about table.dot? Remember, we modified this single case ASH file. And now it's actually not even using any information from my table.dot. We still have to create this file. Why? Because my scripts use the file to know how many things to compute. So we have to create a file which has 400 lines if you want to make 400 computation. So I do a very simple script. Let me just copy. So I'm going to copy my for loop. But now it doesn't matter what I put there. Could be the stuff I already put, or maybe I just put just line number, $I. Doesn't, or could be the same number. Doesn't matter. What matters in this situation, that table.dot has 400 lines, so there will be 400 executions. So we modified this file. I don't have to touch this file. So I believe I'm ready to run this more advanced mode. And let's try to submit. Submit.run, let's say we'll try 16. And I think I've done everything I had to do. Let's see if it's the case. All right. There are 16 running jobs. Let's wait. It takes at least 10 seconds for the first one to be computed. And while it's doing, let me draw your attention to other things going on. All the standard output goes to a single file per meta job. So if meta job computes many different computations, it's going to be just appended. So everything will be inside this standard output file. The exit statuses are all stored in this file, status dot job ID. And again, 1 per meta job. So it's very efficient in terms of using not many files. It's using very few files, as few as it can. So standard output once per meta job and exit status 1 per meta job. And as you can see now, I started producing output files where it's only 1 per meta job. So there will be no 400 outputs. There will be only 16. There are 60 meta jobs. There will be 16 output files. And you can see what's going inside. And it's been appended now. As before, you can do something like this. If you want to see all the results. But the dramatic improvement here, if you have to run hundreds of thousands of millions of computations, this is the only way to do it. The improvement is there is only 1 output file per meta job. All right, there is one final thing I want to demonstrate before we are done. I'm going back to my first farm, which has been computed at this point. And when it's computed, it tells you the whole serial farm is done. I want to redo it. And I'm going to use clean command. We'll delete all my computational results except for input table.dot. It's asking you whether you want to delete all of this. Then it's going to delete all of this file. So we're back to initial state, but with table.dot is already there. By the way, don't be surprised. After you run farm, you look inside your table.dot, you will notice there is one more column which contains the line number. The code works either way. You can add these line numbers by hand, or you don't have to. The code will figure it out and it will do it for you automatically. So it just for your information. What I want to demonstrate, I want to add some bugs. I want my code to crash. So, and the way to do it, I'm going to say like this. So it will try to write to a root file, and it can't. There will be segmentation fault. Let's say I'm going to do it twice. And now I want to redo it. My farm, I'm going to say submit.run, let's say 16. And I can go back to my other farm and say query. It's still running, it's still 8 running jobs. And my meta 3 is still running. So in fact, some of these jobs will be waiting. I have only 32 cores reserved for me, but this is fine. As I explained before, not all of the meta jobs have to run to process everything you need to process. Oh, in fact, it's all of them are running. So what I want to demonstrate the status. Before I showed all the status were 0. So let's get to the point when there is a bug or typo in your initial conditions. So there will be non-zero at some point. So we'll have to wait a little bit. I just want to demonstrate the final features. So I'm running status still. I haven't reached the point where it's crashing. Let me check my other farm. Still running. And my other farm still running. Okay, I reached the first point. So I'm using -f status. So it lists all non-zero statuses at the bottom. So it tells me the line number 103 from my table.dot. So I use Alt-G command in my nano editor. Was it 103? Yes. Voila. So sometimes your problems are as easy as this. You go to that line, you see there was a typo, you fix it, you save it, and then you can use resubmit. Otherwise, if you keep using resubmit, it will always tell you there are a couple of things you need to recompute. So, which is not great. It's full automated, but still you want to try to address the issue first. Let's see. Okay, there is a second one. We reached the second point, and now we're gonna kill. It's still computing other things. So I have 2 issues now. First, there are a couple of things which are crashed, non-zero exit status, and also it hasn't finished processing all of my cases. So 163 LG 163. So I'm fixing this problem. And now if I do query, it tells me there are still things to be computed, and I do resubmit. Let's say 16. For some reason it's slow. Okay. So it tells you what it's doing. So resubmit all the things it needs to compute still. While waiting, we can double check what's going on with the other farm. Okay, the whole farm is done. So which means there are no failed jobs, no missed jobs. Everything has been computed with zero exit status. So you're good. And my third. Again, so it gives you this helpful tips about the status of your computation. Schedule became slow. So it's running 16 meta jobs, processing things which haven't been computed yet and things which failed. And you didn't have to do any editing. You didn't have to delete anything here. It keeps adding new subdirectories and new results. And you keep using resubmit, fixing things, resubmit again if necessary. At some point, everything has been computed. And at some point, you see, hopefully, this message. We are approaching the end of this presentation. If you need more details, please consult the Meta Package wiki page, which is hosted on docs.computecanada.ca. The way I find this page, I just Google for Compute Canada Meta. This is how this wiki page looks like. As you can see, it's very long, and it has topics which were not covered in my presentation due to lack of time. For example, how to do multi-threaded farming, MPI farming, GPU farming, some specific Fortran users examples, and a long section dedicated to troubleshooting, all the warnings and errors you might see and how to fix these issues. If you still need help, you are welcome to submit a ticket to support@computecanada.ca. Please mention my name, Sergey Maschenko, I'm the developer. So this will be assigned to me and I will be able to help you. Thank you very much for your attention.